Assalamualaikum and a very good day to Puan Sadati and my fellow friends. We are from BLR 12 and 11. Yes, our course is Electrical Technology and the course number is BLK2364 for assignment set A, and we are from group 1. First of all, I introduce my team members, which is consists of 4 people, including me. Myself, Muhammad Abid Arfin bin Muhammad Sadiq. My metric number is B1124100603. And second, Kabinet Analaki Shanmuga Sundaram B1124100348. And third is Kiran Raj Analaki Rajkumar B1124100432. And the fourth, Konra Analaki Nagarajan B1124100439. Okay, for the first slide, I will be represent. Okay, for the first question, display the simulation output of the circuit in terms of its current and voltage. So we use a multi-sim for create this circuit. So this circuit is a RLC circuit in a series. So we use a AC component AC power source, and R for the resistor 50 ohms, for the inductor 0.15 millihenry, and capacitor is 10 microfarad and 1 ground. Okay, for the test the current output, so we give a connection, we break down the connection, we give a prop the positive prop to the positive V1 connection, and for the negative we have a connection to the resistor, and for the voltage we just give the positive probe to the top of the V1 and for the bottom of the ground for the negative. So the reading we got is 506.403 milliamps for the current, and we also set in RMS value. And for the second voltage, we for voltage we get 162.634 volt, and we set to RMS value. So basically for the series the current are same and voltage is not same. For the of parallel is opposite, the voltage are same and current is not same. Next slide I will be give to Kiran to represent.
Okay, so good evening. My name is Kiran Raj, Analaki Raj Kumar, matrix number B1124100432. So for my ET presentation today, I'll be explaining how the changes in the value of R, L, and C, which are resistance, inductance, and capacitance, affect the output current and power factor. As you can see, for the before circuit and after circuit, the values of the current, power, and power factor are different. So first off, let me start with resistance. Resistance opposes the flow of current in the circuit. Increase in resistance increases total impedance. Higher impedance causes output current to decrease. Resistance does not cause phase shift between the voltage and current. Increasing resistance improves power factor. So power factor remains unity or closer to unity compared to reactive components. As for L, the inductance opposes change in current and stores energy in a magnetic field. Increase in inductance increases inductive reactance. Higher inductive reactance increases total impedance. Increase in impedance reduces output current. Inductor causes current to lag behind voltage. Power factor becomes lagging and decreases. As for the capacitance stores energy in an electric field. Increase in capacitance reduces capacitive reactance. Lower reactance reduces total impedance. Reduced impedance increases output current. Capacitor causes current to lead voltage. Power factor becomes leading. Capacitor can be used to improve power factor in inductive loads. Okay, so for the next up, we will do how to determine real power, reactive power, and apparent power for the load. As you can see, the picture that is attached in the middle, V peak is given 230 volt, frequency 50 hertz, R is 50 ohm, L is 0.515 millihenry, and capacitance is 10 microfarad. So first up, VRMS is V peak divided by square root 2, which is 230 divided by square root 2, we will get 162.63. Angular frequency omega equals 2 pi f equals to 2 pi 50, we will get the answer 4.16 radian per second. Inductive reactance is XL, omega L 314.16 times 0.15 times 10 to the power of negative 3, we will get 0.047 ohms. And for the capacitive reactance, it's 1 over omega C, which will be 1 over 314.16 times 10 to the power of negative 6, we will get 318.31 ohm. So next up, XL minus XC, we will get 0.047 minus 318.31, which is negative 318.26. Impedance and current, Z equals to R plus JX, 50 minus J318.26 ohm, we will get 322.2 ohms. IRMS is PRMS over Z, which is 162.63 divided by 322.2, we will get 0.505 ampere. So now we will be finding real power, which is P equals to I square R, 0.505 square times 50, we will get 12.74 watts. Reactive power Q equals to I square X, 0.505 square times negative 318.26, we will get negative 81.16 VAR. And for the apparent power S equals to VRMS times IRMS, which is 162.63 times by 0.505, and you will get 82.13 VA. So that is all from me. Thank you.
Good day, madam. My name is Kavilan, son of Shanmugam Sundram. I'm from BLR S slash 1 2. My matrix number B11241043. Today I will present my ET assignment about plot the triangle power. For power triangle, represents the relationship between real power, reactive power, and apparent power in AC circuit. As is shown in the image, in the horizontal line, they will be labeled real power P equals to 12.74 watt. For the vertical line downward, labeled it reactive power, which is Q equals to negative 81.1 VAR. For the cylinder line, will be the apparent power, which is S equals to 82.1 VA. Reactive power is negative because the circuit is capacitive. In a capacitive load, a current leads to voltage, so the reactive power is drawn downward in the power triangle. Thus, the power triangle shows a small real power, large reactive power, and an apparent power equal to hypotenuse. The negative reactive power indicates capacitive behavior and which matches the dominance of capacitor in the circuit. For this slide, I will be presenting about to calculate the power factor for the circuit. To calculate the power factor, the given resistance are 50 ohm, inductance is 0.00015 Henry, and the capacitance is 10 microfarad, and the frequency is 50 Hz. To find inductive reactance, we will use XL equals to 2 pi FL, which is 2 pi times with 50 and the 0.00015 Henry inductance, which we will get the inductance reactance 0.047 ohms. For capacitive reactance, we will be using 1 over 2 pi FL. We get 318.3 ohms. To find the net reactance, we will be subtracting XL minus XC, which will be 0.047 XL minus by 318.3 XC. We will be getting negative 318.25 ohms. To find the total impedance, we will be power R square plus X square, which we will get total impedance 322.2 ohms. Finally, we will be getting our power factor. The power factor formula are cos theta, which will be R over 2, 50 divided by 322.2. we will get 0.155. Power factor 0.155 is leading. Thank you, madam.
Uh, Good day, madam. My name is Kuhandra Nagarajan. I'm from BLR 1/1. My metric number is B11241039. So today I'm gonna present about my part for our assignment, which is how to increase the power factor to 1. Power factor is less than 1 due to inductive loads causing current to lag voltage and producing reactive power. To increase the power factor to 1, a capacitor is connected in parallel with the inductive load. The capacitor supplies leading reactive power that cancels the lagging reactive power of the inductor when inductive reactance equals capacitive reactance. The net reactive power becomes zero. As a result, voltage and current are in phase. The phase angle becomes zero and the power factor reach unity, which is 1. So this is the simulation circuit after power factor correction and compare the result obtained with the circuit before correction. So this is it. As you can see, the before. We analyze the impact of power factor correction on an RLC circuit. We've simulated two scenarios: the original circuit labeled before and the corrected circuit labeled after, where a 1 farad capacitor was added in parallel to the load. So before correction, looking at the top circuit, we observe a highly inefficient power factor. It is very low at 0.155, indicating a large phase gap between voltage and current. So the system is only pulling 12.8 watt. Uh, the total line current is relatively low at 506.4 milliampere because the high impedance of the 10 microfarad capacitor is a 1 microfarad capacitor is limiting the flow at 50 hertz. After correction, the result in the bottom circuit, as you can see, we applied correction using a parallel capacitor C3. The result are significant. For power factor, we have achieved a perfect 1, meaning the voltage and current are now perfectly in phase. Real power, the power delivered to the resistant load has increased dramatically to 5 to 8.9 watt. You'll notice the line current rose to 3.253 ampere. While current usually drops in industrial power factor correction, here it increased because the correction has brought the circuit into resonance, significantly reducing total impedance and allowing the source to drive the load at its maximum capacity. So, for the conclusion, the correction transformed the circuit from a low efficiency reactive state to a purely resistive state, maximizing the real power delivered to the load and achieving an ideal power factor of 1. Um, so, that's all from me, madam. Thanks for listening. Thank you, madam.